Okay, well, hello everybody. Um, Welcome back. And today we are going to continue talking about ANOVA. The last PowerPoint lecture that I uh, had posted for you was talking to you about what ANOVA is and how we compute a basic overall ANOVA. And if you recall, we do an ANOVA when we have one independent variable and one dependent variable, but the independent variable has 3 or more levels, or you're trying to compare 3 or more groups. If you have one independent variable and you're comparing 2 groups, you would be doing some sort of a t-test. But if you are comparing 3 or more groups, then you're doing an ANOVA. So in this example, I thought we would start and refresh your memory on how to do an ANOVA. So I hope you have your calculator with you. This will be the biggest calculation we'll do, and then you'll see as we go through this presentation, much of it you don't need to actually calculate, so that's good. But anyhow, I hope you have your calculator with you so you can see if you remember how to do an ANOVA. And this example is, we had, let's say, mock jurors coming to the research study. They were told they were jurors. They were given information about a defendant and a crime the defendant was supposed to have committed, and then they needed to rate how guilty they felt the defendant was. All the information that was given to the jurors was the same, except in one group they were told that the defendant had a past criminal record. In another group, they were told that the defendant had a past clean legal record. And the third group, there was no background information given about the defendant's past legal history. So in that case, we've got a criminal record group, a clean record group, and a no information group. Okay, so here we have five mock jurors in each condition, and these are their guilt ratings. And if you recall, the first thing we need to do is, like we've done before, find the mean for each group, and then find the deviation scores for each group, and then the square deviation scores, and then sum them up in order to get your sums of squares for each group. So if you would work on that, and pause this now, and then hopefully this is what you get. So we have the mean guilt rating for the criminal record group is 8, for the clean record group is 4, for the no information group is 5, and then we did our deviations, right, which is 10 in this case minus the mean of 8, which is 2. Then you square it. This case 7 minus the mean of 8 is negative 1, and then you square it. Then you add up all the squared deviations, gives you 18. And then you do the same for each one. Now this case we've got a guilt rating of 5 minus the mean of 4 for this group is a 1, and then you square it. A 1 minus the mean of 4 is a negative 3, which you square for 9. Then sum all these up to get these sums of squares. And then same here. This was the mean of 5. Take the score minus the mean is negative 1, square it. The score 6 minus the mean of 5, which is 1, and then square it. Sum those up to get your sums of squares. Oh, and I had forgotten to ask you to find the grand mean. And if you recall, the grand mean is just adding up all 15 scores and dividing by 15. It's what is the mean of everybody in this group. So you add up all the scores and divide by the number of scores. In this case, the grand mean was 5.66. That's the overall guilt rating score for everybody. All right, our hypotheses, as before, the null hypothesis is that all 3 means would be the same. The alternative or research hypothesis is that the null is not true, and we write it out just like that. Degrees of freedom, if you recall, we've got to find degrees of freedom for the between group measure of variability and degrees of freedom for the within group measure of variability. For degrees of freedom between, our formula is k minus 1. K is the total number of groups minus 1. In this case, we have 3 groups minus 1, which is 2. And degrees of freedom within is total number of participants in our study minus total number of groups. In this case, we've got 15 people in this study minus 3. which is 12. So we're looking for degrees of freedom, critical value for an F with 2 and 12 degrees of freedom. And if you go over here to your F table, we've got 2 for the degrees of freedom between, that's always the numerator, and 12 down here, which is degrees of freedom within, that's the denominator. And so with 2 and 12 degrees of freedom, we're at 3.89 is our critical value. Okay, so there's our critical F of 3.89. And actually, I'll just draw this out for a second. We've got a F, critical F of 3.89. Okay, now we've got to do the computations. And remember, we've got our F ratio of mean squares between over mean squares within. Mean squares between over mean squares within, and you've got to find each one separately. I've been starting with mean squares within first because it's just, to me, the simpler one to calculate, so might as well get it out of the way. And before we can do mean squares, we start calculating sums of squares and then divide by degrees of freedom to get us mean squares. So we'll start with sums of squares within, which is adding up the sums of squares for each group. And if you go back here, we've already computed sums of squares for each group. So this is 18 plus 20 plus 26. So 18 plus 20 plus 26 is 64. That is your sums of squares within. And to go from sums of squares within to mean squares within, you divide by degrees of freedom within. And we already calculated our degrees of freedom within. Remember, that's right here, degrees of freedom within, which is 12. So we take 64 divided by 12, and we get 5.33 as our mean squares within, which is the bottom of our F ratio. So 5.33. Sorry, that's not what you want to see. This is what we want. We have an F ratio, which is mean squares between over mean squares within. And we just did mean squares within, which was 5.33. So now we've got to do mean squares between. This is the one that was a little bit of a bigger calculation, which is you add up sum of number of people in a group 1 times the mean of that group minus the grand mean squared. And you do that for all the groups. We have the grand mean. We already calculated it as 5.66. Remember, you could use this formula, but you could also just add up all the scores and divide by the number of scores. To me, that's probably the easiest. So in this case, we're going to start with sums of squares between, which is number of people in group 1, that was 5, times the mean of group 1, which is 8, this is the mean guilt rating score, minus the grand mean, and then square that, plus number of people in group 2, which is also 5, times the mean of group 2, minus the grand mean squared, plus number of people in group 3, times the mean of group 3, minus the grand mean squared. I hope you have your calculator with you so you're figuring this out. What you have to do first is do this subtraction, then square it, then times by 5. Then you do this subtraction, square it, and times by 5. The order of operations is really important in getting the right answer. And if you do that, you end up with sums of squares between as 43.34. Remember, to go from sums of squares between to mean squares between, we divide by degrees of freedom between. So we take sums of squares between, this 43.34, that's from right there, divided by degrees of freedom between, which was 2. Remember, we already calculated that over here. Degrees of freedom between is 2. Gets you 21.67. 21.67 goes here. Then you do your division, and what did it give us? 4.06 is our F. okay? And then this is similar to our T, where you've got our obtained F of 4.06, and it's over here in the tail. It's greater than our critical value of 3.89. So what are we going to do? We are going to make our conclusion and reject the null. Because our obtained F with 2 and 12 degrees of freedom, that's degrees of freedom between, degrees of freedom within, is 4.06, which is greater than the critical F with 2 and 12 degrees of freedom of 3.89. Substantively, we say there is evidence to suggest that there is a significant effect of jurors' knowledge on a defendant's past legal history, criminal record, clean record, or no information on guilt ratings. Okay, so hopefully you recall how to do that. But that's not all, folks. We need to calculate an effect size. We've done effect size before when we were doing our t-tests and our z's. For ANOVA, the computation of effect size is called R squared. R squared, the formula is sums of squares between over sums of squares total. We've calculated sums of squares between before. And sums of squares total is relatively simple because it's all the sums of squares. So sums of squares between plus sums of squares within. We've already done that too. So R squared, in this case, is sums of squares between, and let's just come on over to here for a second. Sums of squares between, which we calculated here, is 43.34, over sums of squares total, which is 43.34 plus sums of squares within, which was 64. So, back here, you've got your R squared is sums of squares between 43.34 over sums of squares total, which is sums of squares between plus sums of squares within, which is that 64, which is 43.34 over 107.34, which gives you 0.40. How you interpret this effect size is that we say this, and this is the sentence you just sort of have to memorize. 40%, that's 0.40, right, becomes 40%, of the variability in defendant guilt ratings was accounted for by the juror's knowledge of a defendant's past legal history. 40% of the variability in whatever the dependent variable is, that goes here, right? In this case, our dependent variable is defendant guilt ratings, but whatever your dependent variable is would go right here in the sentence, and then you say was accounted for by, and then this part is the independent variable, which for us is jurors' knowledge of defendant's past legal history. So what we're saying is those 15 participants all had different guilt ratings, and by knowing someone's guilt rating, we are accounting for 40% of the variability. By knowing what group they were in terms of what they knew about the defendant's past legal history, we're accounting for 40% of the variability in the guilt rating scores, which means what percent is unaccounted for? 60%, right? 100% minus 40% is 60%. So 60% of the variability in guilt ratings we have not accounted for. And you start to think about, well, what else would go into how guilty somebody rates a juror other than what we know about their past legal history? But maybe the juror's own experience with the legal system, or I don't know, how nice the person is, or how ethical they are, or all sorts of things could go into their guilt rating. 40% of that variability is accounted for by what they know about the defendant's past legal history, but there's still 60% of that variability that is yet to be explained. For R squared, here's our conventions: small, about 0.01, medium, 0.06, large, 0.14. So 0.40 is a very, very large effect size. And you probably wouldn't see that in an actual real research study with data that was not made up. Because when we're talking about people, we've got so much variability. If we could explain 6% of the variability, we are really impressed with ourselves. 40% would be unbelievable. Okay, but that's still not all, folks. Your book talks quite a bit about post-hoc testing, and it's an important concept. When we get a significant ANOVA, so all those ANOVAs we've been running, we call those overall ANOVAs or omnibus ANOVAs. When we get a significant result from our overall ANOVA, it tells us that at least one group is different from the other group. But it doesn't tell us which groups are different. In order to analyze patterns of differences between the means, the ANOVA is followed by specific comparisons. There are many, many types of post-hoc testing. The most common ones compare two means at a time. We call those pairwise comparisons, and that's what we're going to do. We're just learning one in this chapter. So post-hoc testing goes beyond the F ratio. If you have a significant F, it doesn't mean that every possible mean is different from each other. So when we're thinking about the criminal record and the clean record and the no information group, what are our comparisons, right? If we're talking about pairwise comparisons, what are all the possible comparisons? Well, we can compare the criminal record group to the clean record group. Whose guilt ratings were higher in that comparison, or are they the same? We could compare the criminal record group to the no information group. Again, is anybody higher than the other in terms of guilt ratings of these two groups, or are they the same? And then the clean record group to the no information group. So we've got three possible pairwise comparisons, and this is what our post-hoc test will do for us. It allows us to look at all the possible combinations, and then we can see which means were responsible for our final F. We're going to use Tukey's HSD test, which is basically doing a bunch of different t-tests. They're a little bit modified. What you do need to remember is that these are called post-hoc tests. Post-hoc means after the fact, or after the event. And the event in this case is your overall ANOVA. You always have to start with your overall ANOVA in order to control our type 1 error. Remember, we don't want this inflated type 1 error rate or too many chances of getting a false alarm, which is a type 1 error. So we first do our overall ANOVA, which we have controlled the type 1 error. We set that at our alpha level of, let's say, 0.05. And then if we don't have a significant overall ANOVA, we stop there. But if you do have a significant overall ANOVA, then we keep going, and then we would do the post-hoc testing. So why are post-hoc tests used? ANOVA only reveals that there's a difference between at least two of the means in the study, but you don't know where they are. So our post-hoc test is used to determine which pairs of means are statistically different from each other. All right, we're going to talk about this Tukey HSD test. I will not ask you to calculate any of these post-hoc tests. I'll show you that I will give you a printout actually from a statistical computer program, and I want you to be able to interpret it, but you will not have to do these calculations, not on a quiz and not on our final exam. All right, in your homework, that learning curve homework, it may ask you to do some of these calculations because I can't take certain problems out of there. So you may have to kind of work your way through them, but again, even if you get them wrong, eventually if you just keep going, you can get your full credit on that. So for our quiz and for our final, you will not have to use these formulas, okay? But basically it's a t-test. Mean of group 1 minus mean of group 2 over standard error of the mean, and this is how you calculate standard error of the mean. It's the square root of mean squares within over total number of participants. And then your book also talks about this harmonic mean, which is if your sample sizes are different, we are not going to do that. You will not have different sample sizes. And then you basically look up in a Q table, so we know how to use an F table and a T table and a Z table. This is a Q table. This is what you use for finding your critical value. Again, you're not going to have to do this for me, so don't worry about it for our quiz or our test. But let's go through some examples in terms of effect size and post-hoc testing. I want to go back to our last ANOVA lecture. Hopefully you remember. And we did 3 examples where we were looking at, these were math test scores. And the first example, we were looking at the effect of school on math test score. And we did this whole ANOVA. We ended up with an F of 0.32. And remember we said, wow, that's a small F, right? There's really very little difference or little effect of school on math test scores. Okay, and if you recall, remember the mean squares between over mean squares within. The between group variability, if you recall, was talking about the difference between the means. The between the means, so 14 to 16.33 to 15.33. How much difference is there between the means? And that between group variability is a measure of your treatment effect, of your independent variable. In this case, there isn't very big of a difference between the means. We don't really have much of an effect of school on test scores. The within group variability, if you recall, is the variability within each group. How much variability is there within groups, school C, or within school B, or within school A? And these are all of the other chance factors, personality factors. Remember, we also call this an error term, everything we don't want to measure. What else goes into children's math test scores? Well, things like their intelligence and their motivation and how they're feeling that day and what they ate for breakfast, and if they got in a fight with their mom before school, things like that. That all goes into their math test score too, and that goes into your within group variability. Everything you don't want to measure. And when we do this ratio of between group variability to within group, you want your between group variability to be large, right? Because that's showing a big effect of your treatment. And the within group variability to be relatively small. In this case, we have the opposite. We have very little between group variability. We have quite a lot of within group variability, and so we did not have a significant F ratio. We can calculate an effect size. Remember, R squared is sums of squares between over sums of squares total. This is your source table. So sums of squares between, which we've already calculated. We calculated this in our last PowerPoint, so maybe you still have your notes on that. But sums of squares between was 8.22 over sums of squares total, which is 8.22 plus 77.33, which is the within group variability. The total is 85.55 or 56. So we're looking at sums of squares between 8.22 over 85.56, which is 10.10. What this is telling us is 10% of the variability in math scores, remember this is your dependent variable, were accounted for by school. That's your independent variable, which means we've accounted for a small amount of variability, but we have 90% of the variability in math test scores still unaccounted for. What about a post-hoc test? I'm sorry, this should say Tukey's HSD. Fisher's is another test, but we're not doing that one here. Do we compute a post-hoc test? Why? Well, we don't, because we had a non-significant overall F test. So we don't have to go further to say, well, where are the differences between the means? Because our overall ANOVA told us there are no differences between the means. So we stop there. Yay. Okay, next one. Now we looked at, if you remember, the independent variable of grade. First graders, fifth graders, and 12th graders. And they all took the exact same math test, and here were their scores. The first graders on average got a 14 on the math test, The 5th graders on average got a 54, and the 12th graders on average got a 92. Okay? This looks like very large between group variability, right? The difference between the means are quite large. And then the within group variability is relatively small compared to the between. And when we calculated our ANOVA, we had an F ratio of 380.33, which was very significant, statistically significant. And we could say, yes, there is an effect of grade in school on math test scores. So let's do our effect size, sums of squares between over sums of squares total. Again, we calculated all these numbers before. Sums of squares between 9,128 over sums of squares total, which is the between plus the within. 9128 plus 72 gives you 9,200, which that division is then 0.99. 99% of the variability in math test scores were accounted for by grade in school, which means we've accounted for almost anything, which makes sense. If I told you that somebody got a 53 on the math test, what grade would you predict they'd be in? You'd predict they'd be in 5th grade, and you'd be almost right 100% of the time. And if I said that somebody got a 14 on the test, you'd think they'd be in 1st grade, and again, you'd be right almost 100% of the time, or 99% of the time. And 12th grade, if you said somebody got a 94, you'd predict they were a 12th grader, and you'd be correct most of the time. Okay. Do we go on to do a post-hoc test? We do, because we have a significant F ratio, and then our question is, well, which groups were different from each other? Where are the differences? Right now, all we know is that somewhere in here, there is at least one group that is different from the others. We have computer programs that do a lot of statistics for us. This is one that does our Tukey HSD for us. And like I said, I'm not going to ask you to calculate any of these post-hoc tests on our final exam, but I might give you a printout that looks something like this. And this is what you need to figure out, okay? This is the different comparisons. This is comparing 1st graders to 5th graders. Okay, we'll just look at this top line. 1st graders compared to 5th graders. The difference between the two mean scores, the mean difference, is negative 40. And that's just taking the 1st grade mean, which is 14, minus the 5th grade mean, which is 54, and that gives you negative 40. So this is the mean difference. 1st graders scored 40 points below 5th graders on average. You don't have to worry about standard error. This is the only other column you have to worry about. So you have to look at the comparison, the mean difference, and then this sig, or significance value. Remember, we have our significance, our alpha level, usually set at 0.05. We say we want things to be significant at the 0.05 level. This column is telling you how significant something is, and for it to be a statistically significant comparison, this column must be less than 0.05. Okay, that's what you have to remember. This column must be less than 0.05. So, is 0.000 less than 0.05? Yes, it is. And so we're saying, hey, this is a statistically significant difference. 1st graders scored significantly lower than 5th graders on this test because this column of 0.000 is less than 0.05. Now we can do this comparison. 1st graders compared to 12th graders. All right, that mean difference is 78 points. 1st graders scored 78 points less than 12th graders. That's what this is telling us. And again, our significance level is 0.000, meaning that all the groups, that group was statistically significantly less, right? Which makes sense. And then we just have to look for the 3rd comparison. So we've compared 1st graders to 5th graders, 1st graders to 12th graders, and what's the one we haven't done? Well, it's 5th to 12th graders. So let's find that. Here are 5th graders, and comparing them to 12th graders is right here. 5th graders to 12th graders. That difference is 38 points. 5th graders scored on average 38 points lower than 12th graders. And again, the significance column is 0.000, which is less than 0.05. So again, we've got a statistically significant difference. 5th graders scored significantly lower than 12th graders. What you can see is that this table is filled with redundant information because it's a computer. It does every possible comparison, so it compares 1st graders to 5th graders. And then down here it compares 5th graders to 1st graders. It's the same comparison. You can see it's just the opposite direction. So in one case it's negative 40, right? 1st graders scored 40 points less than 5th graders. And here we've got 5th graders scored 40 points more than 1st graders. It's the same thing. All you have to do, so there are 6 comparisons here. You need to look at 3. You need to look at the 3 that are different. 1st to 5th, 5th, 1st to 12th, and 5th to 12th. You don't want to compare 1st again to 5th again to 1st. You don't want to do them all 2 times. Okay, so what are we saying here? First, compared to 5th graders, we say that we reject the null because our P of 0.000, and when you've got something that says 0.000, it's not saying, this is your chance of a type 1 error. So this looks like it's saying to you there's a 0% chance of a type 1 error. But of course that's not possible. You always have a chance of making a type 1 error. Anytime you're using a sample to represent a population, you have a chance of making a type 1 error. What's happened here is this was a very, very, very small number, like 0.0000083, and the computer rounded it to 3 decimal places. So it looks like 0.00, but it's not. And by convention, we always change this into less than 0.001, meaning a very small chance. So statistically, we reject the null because our obtained P of less than 0.001 is less than our critical P, and remember our critical P is usually 0.05. If we say test this at the 0.05 level, then that's our critical P, and this is less. And what we're saying is 1st graders scored significantly lower than 5th graders on the math test. 1st grade versus 12th grade, again we reject the null because our obtained P of less than 0.001 is less than the critical P of 0.05. And what we're saying is 1st graders scored significantly lower than 12th graders on the math test. And then the 5th graders versus the 12th graders, again, statistically we reject the null because our obtained P of 0.001 is less than the critical P of 0.05. 5th graders scored significantly lower than 12th graders on the math test. Okay, so in this case we did have the situation where every mean was different from every other mean. Okay, doesn't always happen. So let's look at the last one example we had done last time. This was looking at all 1st graders, and we looked at how they studied for the math test. Did they study alone? Did they study with a friend? Or did they study with the TV on? And here were their means. So studying alone got a 14, studying with a friend 16.33, and studying with the TV on, the mean was 6. And when we calculated our F ratio, it was 13, and this was statistically significant. And if you can even look back at the PowerPoint, but the conclusion is that type of studying, alone, with a friend, or with the TV on, affects math test scores. That's our overall ANOVA result, but it doesn't tell us which group or groups are different from each other. Okay. So we can calculate our effect size first of all. Sums of squares between over sums of squares total. So sums of squares between is 176.22 over sums of squares total, which is between plus within, which gives you 216.89. So 176.22 over 216.89 is 0.81. 81% of the variability in math scores were accounted for by type of studying. Okay, now on to our ANOVA. We're doing our comparisons. we're looking at studying alone versus studying with a friend. Studying alone versus studying with a friend, there's a 2.33 point difference in math test scores. And remember, we're just looking at 14 minus 16.33 gives you negative 2.33. And you don't have to calculate it, you just need to understand it. Here's the significance. This is the other column that's important. 0.55. Is this less than 0.05? No, it's greater than 0.05, which means this is not statistically different. There's no difference in score between studying alone versus studying with a friend. And so here you can see statistically we're going to fail to reject the null, or we can say accept the null, because our obtained p, oh I didn't get that one right, sorry, of 0.550, that should say 0.550, is greater than the critical p of 0.05. There's no significant difference in math test scores for first graders studying alone compared to studying with a friend. It doesn't matter. You can study with either alone or with a friend, and we don't see a difference in test score. Now I'm going to do this with you really quick because I'm sorry that these are wrong. So that was 0.55. So that should be 0.550. What about here? Studying alone versus studying with the TV on. We'll kind of look at this together because I don't know why I made a mistake on these. Studying alone versus studying with a friend. Or studying alone versus studying with the TV on. So let's look. Studying alone versus studying with the TV on, there is an 8-point difference. Studying alone, you scored on average 8 points higher than studying with the TV on. And that significance value is 0.02. Now, is 0.02 less than 0.05? It is. So we're going to reject the null because our obtained p of 0.02 is less than the critical p of 0.05. First graders who studied alone scored higher on the math test than those studying with the TV on. So that's looking here at this comparison. Studying alone, studying with the TV on, there's an 8-point difference, and 0.022 is less than 0.05. So we're saying, yep, there is a statistically significant effect. So we've looked at studying alone compared to studying with a friend. We've looked at studying alone compared to studying with the TV on, but now we've got this comparison to do. Studying with a friend, studying with the TV on. So that's here. Study with a friend compared to study with the TV on. Now you've got a 10-point difference. And is that statistically significant? Is this number here less than 0.05? 0.007 is less than 0.05. So 0.007. We're going to reject the null because our obtained p of 0.007 is less than the critical p of 0.05. So first graders who studied with a friend scored significantly higher on the math test than those studying with the TV on. So what this is showing us is that not all the means are different from each other. You could study alone or study with a friend, no problem, that you don't get any significant difference. But where is the problem? Seems to be studying with the TV on, right? Studying alone compared to studying with the TV on, big significant change. And studying with a friend versus studying with the TV on, again, significant change. So it seems to be that studying with the TV on is what really impacts scores. Okay, let's do, we already did the R squared for the guilt rating study. That was 40%. But let's look at the post-hoc, which is here. Because we had a significant F, we can go on. So let's compare criminal to clean background. Why don't you look at this for a second and see if you can figure out which are statistically significant comparisons and which aren't. And if you've done that, criminal background to clean background, that's a 4-point difference. They rated the criminal background group, rated the defendant 4 points more guilty on average than the clean background. the significance level of 0.04 is less than 0.01. I mean, sorry, 0.05. Less than 0.05. So we're rejecting the null. We reject the null because our obtained p of 0.004 is less than the critical p of 0.05. Jurors who were told that the defendant has a criminal record rated this defendant significantly more guilty than jurors who were told that the defendant had a clean record. Okay, going back here. Criminal background to no information. There was a 3-point difference. And is this significance value less than 0.05? It's not, right? 0.14 is greater than 0.05. So this is not statistically significant. Criminal background to no information. This is not statistically significant. So criminal to no information, we're failing to reject the null, or we're accepting the null because our obtained p of 0.142 is greater than the critical p of 0.05. There was no statistically significant difference in guilt ratings between jurors who were told the defendant had a criminal record compared to jurors given no information about the defendant's legal background. And then we've got one more comparison. This is the clean to the no information. So clean background to no information. There was only a 1-point difference. Is 0.77 less than 0.05? Nope. So we know that this is also not statistically significant. So we fail to reject the null, or we accept the null because our obtained p of 0.777 is greater than the critical p of 0.05. There was no statistically significant difference in guilt ratings between jurors who were told the defendant had a clean record compared to jurors who were given no information. So when you look at this, the only statistically significant comparison is between criminal background to clean background. That's where we saw the difference. The other two groups were not significantly different from each other. So that's what this is telling us. All right, we have finished ANOVA. Congratulations. And good luck doing your homework, and we'll see you next week, or I'll be talking with you with our last chapter, correlations. All right, thank you.